Okay, hello, welcome back. Greetings. Good to see y'all. Hello. Yeah, so it's Valentine's Day. That's super duper.
Yo, man, please, someone in.
There's some of these flowers right outside. They're $4. Some of them are quite nice flowers, so I picked one out.
What kind of flowers are they?
I've been with my wife since I was in second year.
Aww.
So we met in our multivariable calculus class.
So sweet.
Isn't that cute? Right?
Derive equations together.
So when we were getting married, we had to make the invites, or like a collage of us stuff. And I said, should I put the first math problem we solved together on the thing? And she's like, you remember? And I was like, yes, of course I did.
What was it?
It's actually a question in this course, if you're really curious. We're not totally there yet, but we will get there soon.
That is the cutest thing. Well, my mom and my dad was like, can you be my girlfriend? I was like, no. And somehow, he got me. But he thinks I think he got me.
Yeah, so the first problem that we solved together in that class, because we were like study buddies, right? And then we lived together. Was to calculate this integral. So we haven't got to integrals yet, but anyway, I just thought that was kind of
That's so sweet.
nice thing. I was thinking of that on the way to
That's so
class
cute.
today. We'll talk about this problem later, but today we've got directional derivatives.
Actually, that's so wholesome. That's what I mean someone in my chemistry though.
Okay, so with directional derivatives, we defined a couple pieces of notation. Okay, so this is the
Hamilton operator or some shit?
yes, it is a Hamilton operator or some shit. Yeah, it's an operator. It takes functions and gives you the vector of partial derivatives of your function. Okay, so this is the gradient. And it is related to partial derivatives in the following way. So the derivative in the direction v is v times our gradient. So this is the derivative in the direction v. Okay, just recall that for directions, we want to have length 1, right? So this is going to be a unit vector. All right, so for a vector of length 1, we get the following formula. So one question that comes up fairly often is what direction increases the fastest for our function, right? We want to make this derivative as big as possible. So the kind of situation where that would come up is say you want to maximize profits, right? You've got some cost function or some profit function, and you want to keep moving in the direction of biggest profit. So we want to maximize this guy. So we've got a way of rewriting the dot product. So we can rewrite our dot product as multiplication, so using the cosine rule. Now we know that this guy's a unit vector, so he's at length 1. Now we want to make this thing as big as possible. So to maximize this quantity, we have to pick a direction, right? We want to find the direction that makes this derivative as huge as possible. Okay, so what can we choose to make this number big? What do we have? Yes, you two work together. Yeah, we can make the theta maximize this thing, and to do that we make it 0.
Or like 2 pi.
Or 2 pi. So to maximize this, we maximize cos theta. The biggest cos theta can get is equal to 1. Which is the same as theta being 0. Okay, so to maximize the directional derivative, we travel parallel to the gradient. Make the directional derivative as big as possible, you travel parallel to the gradient. Is anyone into machine learning at all? Yeah,
eventually.
Like the 5 machine learning people, yes. So there's a thing called a gradient ascent optimizer. That's this gradient. Okay? So in machine learning courses, like if you go on Coursera, they'll do a whole unit on gradient ascent optimizers. That's this guy here. So I want to go back to that visualization that we were doing at the end of last lecture and look at it with fresh eyes. So at the end of last lecture, we looked at the paraboloid, my favorite graph. Right? And we added the gradient vector field to this plot. Oh gosh, what have I done here? Oh no. Okay, good. We've got our level sets, we've got our graph. Okay, cool. So there's a lot of structure in this picture. There's a lot of stuff going on in this graph. And I want to slowly think about what is going on and what these things mean. Okay, so we've got the graph of the paraboloid. Right, that's this bowl-shaped thing. Now we've got the level curves. So that's where we take this and we cut it into slices. So we've got our paraboloid. Okay, now imagine that you were standing inside that paraboloid. You know, it might help to like make a little paraboloid with your hand and look inside. Or like it's a cup. So you are standing somewhere inside this bowl. And you want to travel outside the bowl as fast as possible. Right? So what you do is you go up the sides of the bowl directly. Right, you're standing in here, you want to go up the side of the bowl to escape as quickly as possible. Okay? That's what the gradient vector field is highlighting. It's highlighting the direction of travel that makes things grow the fastest. Okay, so if we look at this from above, if we look at this from above, we can see that those gradient lines are going out of the bowl quickly. Right? They're all pointing away from the origin. Okay. Given this picture with this cosine theta and stuff, what's the directional derivative parallel to a contour? Let me write that down. What happens if we are, so there's like 3 dudes who are all Googling it right now. I encourage you to come up with the answers quickly. Yeah? What happens if you take a directional derivative parallel to a level curve? Right? Maybe stare at your hand for a second like this. Talk yourself into it. If you're taking a directional derivative along one of these contours, what happens? Or to think of it in a slightly different way, if you're on a level curve, how much is your height changing? 0, right? Your height is not changing if you're on one of these level curves. Right? So if you're going around a level curve, your function is experiencing no change. Your function is constant. So if you're parallel to a level curve, That means that our function's constant, which means this guy's 0. So if you live on a level curve, your function's not changing, your directional derivative is 0. Thoughts there, comments there? Guys who are Googling it, does it match? Yeah? Could you send me a link? Okay, cool. Please do. Yeah. Yeah, so if you're on a level curve, your function's constant. Notice that these guys are perpendicular. These guys are perpendicular to the level curves. Our gradient vector field, the gradient vector field, these guys, is always perpendicular to the level curves, which means if you head in the direction of the gradient, you're switching level curves as fast as possible. So, big point. Okay. I want to see where we are in our book. Okay, so we've introduced this notion of the gradient. And then this is the sort of theorem that we've just talked about. So if you're oh, look, it's the exact same thing. Okay, so let's actually just do one of these maximal things.